upstream until we're outside of the influence of the culvert. Measure the elevations of the bottom of the pool and connect the dots like I showed in that diagram yesterday. And the elevation where it crosses our road when we connect those dots, that's where the stream bed really wants to be. So when we restore this to something more natural, we would give that number to the person who's running the excavator and say, this is where the bottom of the culvert needs to be at this elevation. And then they all know how to set an elevation, and they use a little laser level there, and they dig down to that elevation and put the culvert in there. Then it's set where it's supposed to be, not where it happens to be at the moment. And again, that becomes very important if we're installing a culvert that doesn't have a bottom in it, like a bridge or a bottomless arch culvert, because once we open this stream up back to the width it was supposed to be, it's going to start to try to fix itself by moving the sediment that accumulated upstream, downstream again, and reestablishing that conveyor belt of sediment movement from high elevation to low elevation. And when it does that, if you have a structure without a bottom, what you can do is scour out the footings, and then you can have a structural failure of your stream crossing, which is really embarrassing, having had that happen a time or two with things I've installed over the years. You don't want to have to go back and repair that. So that's why getting the elevation is so critical, and setting your structure where it's supposed to be, because the stream is going to readjust itself once you open it back up to the width that it was supposed to be. Because then at those high flows, it's not going to back up there anymore. It's going to pass all the water through the culvert and move the sediment it's naturally supposed to move. Okay. So a good example of, not really a stream, but it illustrates many of the things you would see if this actually was a true stream. Okay, let's follow this down and we'll see where it comes out into the main brook, and then we'll take some measurements on that. Standing off campus, which is long lawn and parking lot instead of forest, and it's draining through this really looks like kind of marine sediment, fine textured soil, not a lot of rock in it. So the channel become what we call inside, so it's sort of sunken down below the general level of the land because of the erosion factors, probably at least partly due to how flashy the stream is. So it's running off a lot of parking lots and lawns and things like that aren't great at soaking up water. So when it rains, a lot of water comes down here at once, and water drops off and comes down here and drops off. It's probably mitigated by some of those retention ponds, with like the one with the cattails. I know this one comes out of another one. So the land use is influencing how this stream behaves. A stream in a completely forested environment, its whole watershed is forested, is going to behave very differently than this one. And that's something we need to take into account in our culvert designs. I showed you the slide of the determining water volume that a culvert has to handle, and where we delineate the watershed, then look at the land use in that watershed, the slope, the soils, things like that. So a hydrologist designing a culvert for this stream is going to treat it differently than one for a stream that's coming out of a fully forested watershed, most likely, because many of those surfaces up there don't soak in water like the forest floor might. So they may need to design a culvert or a crossing that's larger for a stream like this than one that would be in a forested system, just because of the way water runs off of the watershed for this brook. Let's go down here out of the way of the tree, and we'll take some measurements on this and talk about bank full. Crossing over a permanent stream. There is permitting involved. At a very minimum, you need what's called a permit by rule from the Department of Environmental Protection. What's that?
Fish.
Is it a fish there?
Yeah.
Okay. What do we see over there? Yeah, hiding under the bank there. So this is the stream was vision it. Amazing. I wouldn't have guessed that. This thing. Yep.
I don't think it's fly rod worthy.
Yeah, I don't know. Probably. Don't know. So again, our mission to design a stream smart crossing is to try to address those 4 S's. And the first S, and probably the most important of all of them, is that span the stream. So whatever our crossing structure is, we want it to span the stream channel. And ideally, we'd want it to actually be a little wider than the stream channel. The standard that's all you often hear is 1.2 times the bank full width of the stream. And again, the bank full width is where, when the stream is in flood, where it starts to spill out over onto its floodplain, which is sort of where we're standing here. So the key, one of the keys in measuring a width of a stream is not where the water level happens to be at the time that you're there, but where the water level is where it starts to leave the channel and move on to the floodplain. In a deeply incised channel like this, it's a little different. Bank full is probably actually a little bit below what we see here for a floodplain because this stream channel has moved down so much over time. But we can get some indications of where it is sort of by looking at the banks here. So the bridge that was here, this is obviously a structure that would span the stream, right, and more. It had little abutments here that were on this side and over on that side. So from a stream smart standpoint, spans the stream. The slope of this, all the stream bed channel underneath it was obviously natural. Usually do, unless you've done something like constrict the stream channel underneath them with riprap or something like that. So bridges are almost always a good solution from a stream smart point of view. Excuse me. Oh, geez. So let's take a look down here, and we'll look at some of these bank full features.
Are we staying on this side, Keith? You want to come over?
You can stay here.
Oh, yeah.
I'll throw and cross you. Yeah. What's that? Yeah, there's a little bit of brown ash on here. The right kind of soil for it.
Yeah.
Again, bank full. We're looking at where the water is going to start to spill out of the banks, and you can actually see on this side where the water's come up and washed away some of the leaves here in a recent storm event. So originally I thought the bank full might be down below, actually down below the bank here, but the more I look at this, there's some indicators that indicate that bank full is probably actually up here somewhere. So some good indicators in an undisturbed system. What you would look at is what I call the point bars, and this. So basically, where the land comes in a bend here on the inside of the bend, you'll get sediment deposited, and where the slope of that sediment rapidly changes, that's a good indication of where bank full width is or bank full elevation. Another one, in a stream like this, is sort of where this moss grows along the edge. That can be an indication of bank full width as well. And streams are variable, right? They're not rule or straight on either side. So when we measure bank full width, we need to measure in several locations to be able to, and then sort of take an average, and that'll give us our stream width for when we design our crossing structure, whether it's a culvert or a bridge or anything else. Again, we want to span the stream, and that'll give us the number we're trying to span with whatever structure we put in there. So let's take a couple measurements. I'll just throw the tape across here, and John can grab it. And we'll see what we got. So I would hold this right about where your toe is, right there. Maybe over here. So right here we've got a width. If I go to right about here, of about 8 feet. So that's one measurement. And then we can come down here. Probably drop down a little lower here. Yeah, exactly, right to there. That's 9. We'll come up here and do one.
Green frog. That's like green frog? Oh. Green frog? You got that on video?
Right up under
We got about 8 feet there. So we would keep doing this, maybe take 10 or 15 different measurements up and down the stream and get sort of an average. But it looks like, it doesn't look like much of a brook, but it's actually about 8 feet wide. The bank full width is about 8 feet. So that means whatever structure we put in here, we want an 8-foot span if we actually wanted to make this stream smart, to not have the structure unduly influence the stream as it passes underneath it. 8 foot is a huge culvert. We probably wouldn't want to put an 8-foot round culvert in here. The problem with round culverts is they're also very tall. They're as wide as they are tall, right? So you need, if you're putting a road over it, you need a whole lot of fill to cover over the top of it. So that's where you start to think of some of those other structures, like an arch culvert or a little bridge or one of those squash culverts that's wider and a little bit lower that you could actually embed down into the stream channel in a brook like this. So that's where you start to kind of look at the whole toolbox of what you have and figure out what's going to be most cost effective for your situation. That trail there with the little bridge, that was probably very cost effective to do. Put a culvert in and put fill in or something like that for a trail. This doesn't make a whole lot of sense if you can get away with something else. So I sent along that link that has some information on all the different types of crossings that are out there, and you want to use sort of the whole toolbox. But that's basically what we do when we design one of these, is we do that profile to get the stream slope, figure out where the stream elevation is, figure out the bank full width, and then design our structure from there. Any questions on that? So other things to look for, we had a tributary coming in there where I'd be measuring my width. If I'm going to have my culvert down here, obviously I don't want to measure widths above that, right, because I have more water coming in. So you want to be aware of that. In flat channels like this, sometimes they can become braided, so you may have little islands in there, and you sort of have to combine everything to get the proper width for the crossing that you're designing. So there's a little bit of art to it as well as science. Any other questions? Anything else you'd like to cover? We'll take a walk up and see where this is actually coming out, and it'll be sort of illustrative of what is actually feeding this. You find more fish?
That's no problem.
Okay, good. So aquatic organisms. We tend to talk about fish because that's what everybody thinks of. But there's a whole lot of other stuff that uses the riparian corridor too, right? So amphibians, terrestrial mammals that may move along the bank. If you have a busy road, having some dry banks actually inside the culvert that mink or something could scurry along instead of going over the top of the road can be really important as well. So those are things to consider as well, because it's not just the fish. there's a whole lot of other stuff going on in the stream. There's a whole lot of other stuff happening in the riparian corridor. Yeah, John, you have a question?
What are some things you look for when you decide where you're going to put your crossing?
That's a good question. If we're replacing a crossing, oftentimes the road is where it is where it is, and we're kind of stuck to that spot. But not always. If you have a trail or like a logging road or something, sometimes it's pretty easy to move those roads to another location. So generally, the things we're looking for is a place further to the stream. If you approach on an acute angle, your culvert has to get longer to get the side fill that you need to keep it from collapsing into the brook. So a right angle approach if we can. Here we don't have it, but places where you have nice, hard, stable banks, so rock or something like else like that is going to not erode very easily, because even a properly sized crossing at really high flows will constrict the stream channel some in a big flood. So we need to look for stuff that's stable. And those are the two main things. Try and look for a narrow spot if you can find one. But you know, stable banks, stable bottom, and a place we can cross perpendicular to the channel are things we look for. Yeah, good question. The other reason you want to cross perpendicular is you want to do as little disturbance in the riparian area as possible, because that's a sensitive place. And if you're on an angle, you sort of extend the time you're in the riparian area, just because of the nature of the geometry of it. You've got to have a longer piece of road in the riparian area as opposed to crossing at a right angle, getting in, getting out the other side. This is if we were to use a round culvert here, this would be a good place we could embed a culvert, because the soil is very easy to dig into here. It would be mobile. It would move into this muddy bottom would move into the culvert, and if we sized it right, it would probably stay there. Sometimes if you're in really rocky streams, it'd be hard to actually physically dig into the substrate to embed a culvert, but this is a place we could do it fairly easily. When it actually comes to construction, one thing we want to do is manage the amount of sediment we create, the disturbance we create in the stream. And the way to do that, say we're putting a stream crossing in here, basically what you do is you build a dam upstream and then put a pump in and pump the stream water around your work site and put it in again downstream, because you don't want to de-water the stream. You can't do that. So you've got to get the water down there, but you don't want it moving through your work site as you're digging and putting in footings or all those sorts of things, and stirring up all that sediment and moving it downstream, because you don't want to do that. So if you work what's called in the dry, a little coffer dam, pump around to the other side, make sure you armor where the pump is coming out with a rock or something like that, so it doesn't erode the bank. That moves your water around the side. Then actually in the hole itself, so you've got this dry spot, or mostly dry spot, you're still going to have groundwater seeping in. No dam is perfect. Water is going to be seeping in, so you put what's called a mudsucker pump in the hole itself. That's a diaphragm pump, and you pump it up into the wood somewhere. Build a square of hay bales with some geotextile fabric and pump it into that, and that basically filters out the muddy water coming out of your hole and lets it slowly drain back into the stream nice and clean. That also makes construction much easier if you're working in a dry hole instead of a bunch of mud. When you take a bite with the excavator, you actually get ground instead of a bunch of slurry, and the excavator people really like that. So that's a technique for working in the dry. And depending on your permitting, that's oftentimes required, that you have to isolate your site from the stream, do your construction. Then at the end, you slowly pull that coffer dam, and you basically have one little puff of sediment that comes through as the water is going through the first time, and reestablishes the stream through your crossing. That's just some of the construction details. All right, Any other questions? So you can see that, I mean, just looking at even this brook, even though it isn't the healthiest stream out there, there's lots going on in here. You've got banks that are undercut, where we saw fish hiding. You've got areas where the water's moving a little faster. You've got deeper pools. There's a lot of different, there's a lot of diversity within the stream channel itself. And that's what the organisms have evolved to make use of. A pool here, a fast area here, a bank to hide under. And that's why culverts are so foreign to many organisms. It's a 70-foot section of exactly the same type of habitat moving in exactly the same way, and that's not what fish and other organisms were evolved to deal with. They evolved to deal with this, a little piece of this, a little piece of that, a little piece of that. That's why, a continuous flow going fast through a 70-foot metal pipe is something very foreign and was not in the evolution of the organisms. So sometimes that's why they can't deal with it. Fish have different muscle groups, and they have one that basically lets them swim at a very fast speed, but it's only for a very short period of time, in that swimming at what they call a burst speed. And if they don't have enough energy to have a burst speed to get all the way through the long culverts, that's when you get those barriers. But they did not evolve to deal with that kind of structure. If culverts were a naturally occurring phenomenon, fish probably would have evolved to get through them. Yep.
Could you design culverts to have lake-to-waste habitat?
Absolutely. There's a whole class, it's like a 4-day class the U.S. Forest Service puts on. It's called Stream Simulation Design. And what they actually teach is how to install a crossing and then construct a stream channel in that so it mimics the natural stream bed. And there's all kinds of, and it gets very involved, but there's all kinds of measurements you take of the natural stream bed. You actually do some inventory of the rock sizes. It's called a pebble count. So you measure a subsample of the rocks, and then you actually recreate the stream channel in your crossing. Yep, absolutely. That becomes more and more important as your streams get steeper and steeper and steeper. These low gradient streams, it's pretty easy to bed a crossing or put a bridge in or something like that, and have it work okay. But as you get into steeper terrain, stream simulation design is really becomes important. Yep, great question. And sometimes even in the round culverts, we'll just, it's not stream sim, but we'll just chuck some rocks in there, and that will slow down the water and create a little bit of roughness and diversity and things like that. When I used to do workshops with this, the last thing you have to do for a arch culvert is armor the footing, so you got to put rock up against the footing so the footings don't wash out. And before I gave everybody their continuing education certificate, I made them call in and throw rock on the footings when we were doing culvert classes. It's a good way to get people to stay to the end and throw rock. Okay. No other questions? Let's wander up this and see where it comes out of the woods and see what's actually feeding this thing. But again, lots of diversity in the stream channel. Places for stuff to hide, places that slow down the water, places that speed up the water. Yep.
So deadwood's an important habitat feature, add deadwood.
There are cases where we add deadwood, particularly to streams that have been altered by log driving. Most of our wood up until the mid-1970s was transported to the mills via river. Anyone know when the last log drive happened? 1976. Not 1876, 1976.
Wow, that's impressive. That's
On the
much
Kennebec.
later than I would
Yep,
have
that was the last drive in Maine. And if you were trying to drive wood down to a mill, would you want all this kind of stuff in the way of your log drive? No. So what they did is they ran a bulldozer down the stream beforehand and straightened out the curves. A lot of times, if there were bends in the streams, they'd put rocks across them and we don't want the wood going over there, we want the wood to shoot down the stream, which was perfectly legitimate for what they were trying to do at the time, but had big effects on habitat. So in order to help restore some stream processes in some of those log-driven streams, there are some efforts to move rocks around in those streams again and add trees and wood back to the stream to increase diversity of the stream channel. Because a log-driven stream that's 4 inches wide and 4 inches deep and one D8 blade wide, which is what they tend to be, don't have a lot of this habitat diversity in them. So adding wood into streams, you don't just go and do it. You need to figure some stuff out beforehand and work with your biologists and figure out if it's a place where it's actually needed. And then there are some benefits to putting wood back in streams. Yep. Yeah, the last drive was on the Kennebec in '76. What ended the log drives? This is interesting. This is history. This is good stuff. So the Clean Water Act is what ended log drives. But interestingly, what that required us to do in the woods was build a whole ton of roads and a whole ton of stream crossings. So a lot of our culverts up there in the big woods date from the mid-1970s when we were building road like crazy because we couldn't send wood down the rivers anymore, and because we were having the spruce budworm outbreak, so we needed to cut a lot of wood anyways. So that was actually an unintended consequence of the Clean Water Act, was the roading of the North Woods and the stream crossing infrastructure that came with it, which had some problems. So there's always big things like that. There's always unintended consequences that come with them. Not saying the Clean Water Act was a bad thing. The Clean Water Act was a great thing, but one of the consequences was shifting from moving wood down rivers to moving wood more on roads. There are other reasons that happened as well, but that was the real driver. That was 1973 Clean Water Act, and by '76 we were done with the log drives.
You described a process of channelization, basically. That's not just in the woods, but in agricultural areas,
Yep.
urban areas. Was there any attempt to restore any of that, like to undo the channelization?
Yep, absolutely. That's a very widespread restoration technique, because up until we really started to think about the other processes that were going on in streams, a lot of our human needs were to move water away from places we didn't want it as fast as we could. And a channelized stream, so one we take the bends out of, ones we take the debris out of, moved water very efficiently and served our goals such as they were on the land. But as we learned more about how streams work, we learned that we were having really big negative impacts on the stream systems. A lot of this stuff, it wasn't malicious at the time. It was where we were at that point in history, and what we know has evolved since then, and we've learned more about how streams work. We used to teach people to put culverts in to do as least disturbance to the stream channel as possible. So you knock a few rocks out of the way, be very careful not to disturb the banks, plunk the culvert in and cover it up. And we thought that was the best way to do it. But what we didn't think about was all this constricting the stream, setting the culvert too high, having something the fish has to jump up into. And what happened was we learned more about how streams work, and then realized the guidance we were giving wasn't looking at the whole picture, so we changed that guidance as we learned more. So, a lot of this stuff, it wasn't malicious, we learned more about how streams function, and that's true for many things. Okay?
Keep going?
Yeah, good segue for the Clean Water.
Yeah.